An ancient natural nuclear reactor assumed to have existed for millennia sounds like a myth. Maybe because the term reactor usually implies a man-made structure, but in this case, the reactor is a region of natural uranium within the Earth's crust in Oklo, Gabon. The element uranium is naturally radioactive, and the conditions in this rocky area just happen to be right to cook up some nuclear reaction. Join us as we delve into this mysterious scientific anomaly that has left scientists puzzled over time. Over the years, scientists have made many discoveries revealing mysteries that have shocked many. But this particular discovery is unbelievable yet real. Nuclear reactors are not something you just stumble upon by chance, yet this ancient natural reactor has been around for millennia. This mysterious, naturally occurring scientific anomaly was discovered in 1972 when some French scientists were testing uranium content in a uranium enrichment plant. They noticed a strange deficit in the amount of uranium-235 they were processing. In a uranium enrichment plant where every gram of fissionable material has to be carefully accounted for, this is a serious problem. The problem lies in the ratio of uranium isotopes in their samples. Typically, uranium ore is made up of 3 different isotopes, each one with a different number of neutrons. Uranium-238 is the most abundant, uranium-234 is the rarest, and uranium-235 is the particular one that nuclear scientists are most interested in because it can sustain nuclear reactions. Researchers soon traced the anomaly to the uranium ore from Oklo, Gabon in West Africa, which contained far less uranium-235 than the ore obtained from anywhere else on the planet. Scientists are not so happy about this problem, which prompted France's top nuclear scientists to conduct further investigations, and they found out that the problem was linked to uranium-235. Naturally, one would expect to find that uranium ore is composed of 0.720% uranium-235, since that is the percentage found in other rock samples from the Earth's crust, the Moon, and even meteorites. However, scientists found something fishy. The uranium sample only contained 0.717% of uranium-235 in relation to the normal value of 0.720%. One might think a minor variation of a mere 0.003% is insignificant, but with regard to uranium, it is the other way around. This implies that back at the mine, around 200 kilograms of uranium appears to be missing. It hadn't been lost or stolen. Instead, it was revealed that the missing 0.003% had undergone the process of nuclear fission and split into other atoms. However, this conclusion does not sit well with experts. Scientists have struggled to create a nuclear reactor, and it seems unlikely that nature just happened to create one purely by accident. This phenomenon is unlikely, but not impossible because it actually happened. Since the discovery of the ancient Oklo reactor, it has been a significant driver of important research in nuclear physics. Particularly, scientists have used it to study how buried nuclear waste might spread through the environment. Since the reactor began operating 1.7 billion years ago, they have also used it to study how the universe's fundamental constants may have changed during that time. A naturally occurring nuclear reactor is a rare find, almost unimaginable. For a nuclear reactor to be activated and function properly, certain things must carefully be put in place. Scientists are puzzled by how one that abruptly occurs in nature met these conditions and functioned effectively at such an ancient period. This motivated them to conduct further investigations to get answers and relieve their curiosity. The first nuclear reactor to produce electricity started in 1951 and only produced a trivial amount of energy. On the other hand, the pile of rock in the ground of Oklo created nuclear power about 1.7 billion years ago. This opened the door to a number of questions from researchers. The first puzzle that scientists had to deal with was how a naturally occurring reactor could work at all. Nuclear scientists were of the opinion that reactors do not work with natural uranium because the level of uranium-235 is too low at only 0.702%. Instead, the uranium-235 has to be enriched so that it is about 3.5% of the total. So how did so much end up at Oklo? And how did it end up as a nuclear reactor? Further investigation revealed some conditions the natural reactor must have fulfilled. The first was owning a good percentage of uranium-235 to fuel the reaction. While 0.702% might seem small, it is enough for nuclear fission. And when the ore samples from Oklo are compared to other samples from all over the world, this was likely the percentage of the natural reactor when it started 1.7 billion years ago. The second condition is a source of neutrons. Uranium-235 decays naturally into another element named thorium. and releases a neutron in the process. This neutron can then move towards another uranium-235 atom and start the fission process. Before you get confused, nuclear fission occurs when an atom breaks apart into smaller atoms, and energy is usually released in the process. This neutron fuses with uranium-235, and together they combine to form uranium-236, another isotope of uranium that is unstable. When overwhelmed with instability, uranium-236 splits, creating a variety of smaller, stable atoms and neutrons in the process. These neutrons can then happily shoot towards other atoms and continue the chain reaction. However, the liberated neurons are high-energy particles that tend to fly away rapidly. So nuclear reactors usually contain a regulating material that slows down the neutrons so they can interact with other uranium atoms. Surprisingly, it turns out that water is a reasonable neutron moderator. An important component to notice around the natural reactor is the presence of water seeping through the uranium ore. This has an interesting impact on the way the reactors operate. Nuclear scientists believe that the Oklo reactors operated in pulses. As water flowed into the uranium ore, it moderated the neutrons, allowing a chain reaction to occur. When the atoms are dividing, they release neutrons as well as energy. The water would slow down the neutrons, but the energy released increases the temperature of the ore, subsequently boiling the water into steam, which then escapes. When this happens, the neutron would no longer be able to interact with and split uranium nuclei. Therefore, the chain reaction stops. The uranium ore then cools down, allowing water to flow back in. This mechanism explains how the Oklo reactor operated in pulses. Today, nuclear scientists have calculated that the chain reaction probably lasted for about 30 minutes and then switched off for about 2 hours and 30 minutes. A pulsating, watery cycle that continued for hundreds of thousands of years. While the natural reactor was on, they were powerful. Scientists stated that the reactors likely operated under conditions similar to present-day pressurized water reactor systems, with pressures of about 150 atmospheres and temperatures of about 300 degrees Celsius. Sadly, all good days are numbered, even for a happy natural reactor. Over time, the levels of uranium-235 got used up, and the level dropped too low to sustain any meaningful reactions. The reactor eventually slowed to a stop, leaving only a few traces behind that it ever existed. Interestingly, the natural nuclear reactors found in Oklo are unique, and up to date, no additional nuclear reactor has been discovered. Soon after the strange uranium discovery, scientists confirmed the basic idea that natural fission reactors were possible for the depletion of uranium-235 at the Oklo site. Irrefutable proof came from an examination of the new, lighter elements created when a heavy nucleus is broken into two. The abundance of these fission products proved so high that no other assumption could be made. A nuclear chain reaction very much like the one that the French scientists confirmed in 1942 had certainly taken place all on its own about 2 billion years ago. Shortly after this remarkable discovery, scientists from all over the world studied the evidence from these natural nuclear reactors and came together to share their work on the Oklo phenomenon at a special conference held in Libreville, the capital of Gabon, in 1975. However, a scientist named George A. Cowman described how some of the neutrons released during the fission of uranium-235 were captured by more abundant uranium-238, which became uranium-239, and after emitting 2 electrons, turned into plutonium-239. More than 2 tons of these plutonium isotopes were generated within the Oklo deposit. However, almost all these materials, which have a 24,000-year half-life, have since disappeared primarily through natural radioactive decay. Nevertheless, some of the plutonium itself underwent fission, and this was proven by the presence of its characteristic fission products. The abundance of these lighter elements allowed experts to deduce that fission reactions must have continued for hundreds of thousands of years. From the amount of uranium-235 consumed, scientists calculated the total energy released to be about 15,000 megawatts per year. And from this other evidence, we're not able to work out the average power output, which was probably less than 100 kilowatts. Experts say this is enough to run a few dozen toasters. Scientists, in their pursuit of knowledge, did not stop at the discovery of the ancient reactor. Further research was carried out to sniff out what might be lurking around in the rocky landscape. French nuclear scientists carried out a detailed survey of the Oklo site and discovered not just one reactor zone, but up to 17 of them over an area of several tens of square kilometers. Some of them were close to the surface and, as a result, were influenced by the weathering processes. Others, on the other hand, were at a depth of up to 400 meters and were more or less pristine. In addition to the depleted uranium-235, these zones contained numerous fission fragments such as isotopes of zirconium, yttrium, neodymium, and cerium. The unusual ratio of these isotopes was an important indicator of what perspired there almost 2 billion years earlier. Moreover, the presence of these fission byproducts immediately piqued the interest of scholars. Perhaps the biggest challenge facing the nuclear industry is to find a way to deal with the highly radioactive waste that these reactors produce. One idea is to bury it, but this raised a number of questions regarding what would happen to this waste over the years, during which it remained toxic. The Oklo reactors were a natural test of this. Subsequently, scientists began a program to measure which different fission products migrated away from the reactor zone. Experts stated that one of the most important yet surprising early findings was that uranium and most of the Earth's rare elements did not experience any significant mobilization in the past 2 billion years. This is because the wastes were perfectly contained in Oklo. It appears it is not unrealistic to hope that long-term disposal in specially selected and engineered geological repositories can be successful. This evidence has since become one of the main arguments in favor of nuclear waste repositories. Earth created a nuclear reactor naturally, long before humans ever existed. The scientific study of this unique natural reactor provides important insights that are relevant to anthropogenic nuclear waste storage. Mother Nature, it seems, knows how to operate a nuclear reactor. What part of the video did you find most interesting? The discovery of a naturally occurring nuclear reactor said to have been in existence even before humans. The unique principles by which the nuclear reactor functioned in prehistoric times. The other discoveries uncovered at the indigenous site, or the proof in the light elements. Let us know in the comments section, and don't forget to like and subscribe to the channel for more videos. Thank you for watching, and we'll see you in the next one.